In 1960, near Lake Ewart, high in the mountains of Central Equatorial Africa, on the border of Uganda and Zaire, a Belgian geologist and archaeologist, Jean de Rezin de Beauquat, what a name, man! Found what we can consider the first evidence of counting, the Ishango bone. And that was about 25,000 years ago, where people, or the Ishango people, were using Ishango bone to count. What they were counting, you may say? Well, there are two hypotheses that explain what it could be counting. Hypothesis 1. Number system. The notches form a base 10 counting system, list prime numbers and show a doubling. Multiplication. Hypothesis 2. Lunar calendar. The notches track a 6-month lunar cycle. Either way, the Ishango bone counts as the first evidence or the first appearance of mathematics. But wait a second, look at it. Do you see a square root? Is there some quadratic equations? Well, not everything started complicated. We can see that in ancient Mesopotamia, the Sumerian people were living in cities. Each city has more than 30,000 to 40,000 people living on it. By just using our imagination, we can conclude that these cities need organization. Tax system. Yes, they also have the tax system, and it is complicated than you think. Also, people in the city were trading goods, chickens, and much more. This makes Sumerians need something to keep track what they were selling and what they were buying. So, they invented Microsoft Excel? What? No. They invented tokens, which are made from clay. The cone, sphere, and the flat disk were used to represent small, medium, and large measures of grain, and probably to count anything else. But wait a second, why didn't they just use woods or bones, like the Ishango bone, to keep track the goods they have? Good question actually. The reason why they used tokens instead of Ishango bone will be clear if we use an example. There is a Sumerian man has 10 sheep. For those sheep, he has 10 disk token to keep track. So, if he sells 4 sheep, he can know how many sheep he still has, exactly by removing 4 tokens. So, he left with 6 tokens, thus 6 sheep. Man, this is subtraction. Yes, it is. And this is why they use tokens instead of bones, because you can remove or subtract using tokens, but you can't remove or subtract the notches from the bone. Over the years and centuries, the Sumerians developed a lot of ways to represent numbers. For example, they put coins into a clay envelopes for safekeeping and then sealed up. But there's a problem. Once you seal the envelope, how could you remember how many coins inside? Why don't we take another coin and make the same number of coins outside the envelope as there were coins inside? It worked. But wait a minute, why did we put the coins inside in the first place? Why didn't we just make the same number we want to represent on the outside of the envelopes without coins inside? Well, that's actually what they did. And these simple markings are actually laid the foundation for cuneiform, one of the first writing systems in history. This is the oldest known clay tablet with mathematical computations, which shows a multiplication table in cuneiform, which may have been used by student scribes to learn mathematics. And it was created around 2700 BCE in Sumer. Also, this is a Babylonian clay tablet called Plimpton 322, was created around 1750 BCE in Sumer. This table contains the Pythagorean triples, integer solutions for the equation a squared plus b squared equals c squared. For example, 3, 4, 5. 9 plus 16 equals 25. And it is 1000 years ago before Pythagoras even existed. Yup, there are a lot of evidence that shows the Pythagorean theorem was discovered by many civilizations before Greeks. Exactly Pythagoras. As we can also see here, this circular tablet from the Yale Babylonian collection called YBC 7289, which shows the Babylonian scribes knew Pythagorean theorem. They were also able to estimate the square root by 6 decimal places, and that was around 1800-1600 BCE. There was no Pythagoras back then. Around 2630 BCE, the ancient Egyptians started to build the pyramids, and as you know, the pyramids are very large buildings, and to build very large buildings like the pyramids, you need a unit to base all your measurements based on it. Ancient Egyptians realized this problem, so they defined their own unit that was based on the length of the man's arm from elbow to fingertips plus the width of his part, and this unit helped them build their big pyramids. Man, the aliens who built them? Maybe. This idea of the unit is what helped to the foundation of fractions. Actually, ancient Egyptians were the first civilizations to use fractions, or proper fractions, which is 1 over something, like 1/2, 1/3, 1/4, and so on. We know the ancient Egyptians used the fractions because of the Rhind Papyrus, one of the most famous mathematical documents from ancient Egypt. It was written around 1550 BCE by a scribe called Ahmose, who is maybe the earliest contributor to math whose name we still know today. The document is roughly 2 meters long, and it contains 84 math problems covering multiplication, division, fractions, and geometry, likely used as a scribe's training text. Now let's jump a bit forward to the Greeks, because really this is where math starts to look like the math we know today. Greek mathematics runs from around 600 BC, starting with Thales, all the way to 529 AD, where the Academy of Athens got shut down. But what makes the Greeks different from Babylonians and Egyptians? Those earlier civilizations were doing math by observation. For example, 6 plus 4 equals 4 plus 6, which equals 10. Actually, this works with any number, so let's make it a plus b equals b plus a, and this is the commutative property of addition. We can see it work by just observing the numbers and trying different numbers, but the Greeks said no, we need actual proofs, we need logic, we need deduction. That's a massive shift. So it starts with Thales and Pythagoras back in the 6th century BCE. Yeah, the actual Pythagoras this time. Thales gets the title of the first true mathematician because he applied deductive reasoning to geometry, and Pythagoras and his followers, the Pythagoreans, actually coined the word mathematics itself. And yes, they linked to the Pythagoras theorem, plus the discovery of the irrational numbers, which again was discovered 1000 years ago by the Babylonians. After that came the classical period of Greeks, where Plato's academy in the 4th century BC basically becomes the math hub of the ancient world. This is where Eudoxus come from, where he developed something called the method of exhaustion, which basically an early ancestor of calculus. Aristotle was around too, and while he wasn't really doing math, he laid the groundwork for formal logic, which everything else depends on. Then comes the Golden Age, the 3rd century BC, centered in Alexandria, at this place called the Museum, and this place stacked with names you've probably heard of. Euclid. I know Euclid, he wrote a great book called The Elements. Yes, The Elements. It is about The Elements is arguably the most influential math textbook ever written. There is also Archimedes, probably the greatest mathematician of ancient worlds. In general, Greeks were interested in geometry and astronomy, so that shifts their focus towards trigonometry. Hippocrates, Heron, Melinus, and then Ptolemy, whose book The Alchemist stayed to go trig reference for like 1000 years. Later on, in the Civil Age, 250 to 350 AD, the Hierophants pushed algebra forward, His work later on inspires format, and then slowly it all winds down. Pappus of Alexandria basically is the last major inventor. Hypatia, the first woman mathematician we have record of, around 420 AD. The Greek myth didn't totally die after that. It kept growing in the Byzantine Empire, but it became more commentary and older work than actually new discoveries. In 529 AD, the Academy of Athens got shut down for good. With it, the Greek mathematics gone. Not exactly. That takes us to the Roman Empire. The Roman Empire was an ancient empire centered on the city of Rome, established in 27 BCE. At its height, it comprised most of continental Europe, Britain, much of Western Asia, and North Africa, covering over 1.7 million square miles. The empire was known for its significant contribution to law, governance, architecture, and culture. Yep, there is no mathematics. The Roman Empire didn't actually improve math, they just keep things ticking because they didn't care about theoretical mathematics. Instead, they valued mathematics for its particular applications, such as trade, land division, and construction. The Roman numeral also didn't help. Take for example the number MDXXVI, which is 1526. Subtract from it the number MMXXVI, which is 2026. If you are familiar with the Roman numeral system and you subtract the numbers I give you using the decimal system, you could tell me the answer is D, which is 500. Man, it's hard to do arithmetic with Roman numerals. Yep, but the Romans weren't doing arithmetic like this. Instead, the Romans used a combination of counting tables, pebbles, and basic reckoning for basic calculations. They did not treat written numerals as a complete calculating machine, but the main use of their numbers is a way to record numbers, dates, measurements, and official values. The main effect that the Romans made on mathematics is that they spread their weak numeral system, and people will stop using the numeral system until the 14th century, when it was replaced by more efficient Hindu-Arabic numeral system. What? Yep. The Hindu-Arabic numeral system was created by Indian mathematicians between the 1st and the 4th century. Indian mathematicians also gave us one of the crucial numbers ever existed, 0. In ancient times, the 0 was used by Sumerians and Babylonians, but not in the way you think of. They were using the 0 as a placeholder. For example, what number is this? 1? No. What? As you can see, I tricked you in this, because I didn't give you the full representation of the number. They are missing zeros, or to be more accurate, these are placeholders, and it is the only way we can use to differentiate between 1, 10, 100, and so on. The number 0 we know today evolved from a placeholder to a number in its own right. In ancient India, with mathematicians like Brahmagupta formalizing its use as a number in the 7th century. In those times, between the 7th and the 9th century, the Arab mathematicians adopted the Indian numeral system and add fraction to it, thus became the Hindu-Arabic numeral system. Thanks to Al-Khwarizmi, the Hindu-Arabic numeral system spread from Asia to North Africa. What? You don't know Khwarizmi? Muhammad ibn Musa al-Khwarizmi, born in 780, was a Persian mathematician, astronomer, and geographer who wrote in Arabic during the Islamic Golden Age. Around 820, he worked at the House of Wisdom in Baghdad, the intellectual hub of the time, basically the place to be if you loved math. His biggest contribution was a book called The Concise Book of Calculation by Restoration and Balancing, or algebra, which means algebra, written between 813 and 833. He laid out the first systematic way to solve linear and quadratic equations. At those times, most of Europe were using the numeral of the Romans until the 13th century, where Fibonacci learned about the Hindu-Arabic numeral system on a trip to North Africa. Fibonacci realized the power of positional notation of the Hindu-Arabic numerals, and it was more efficient and greatly facilitated commerce, much greater than the Roman numerals. In 2202, he wrote his book Liber Abaci, where he introduced both Bayesian positional notation and the symbols known as the Arabic numerals in Europe. The Roman numeral system resisted the Hindu-Arabic numeral system until the 15th century. Unlike Roman numerals, calculations are easy using Hindu-Arabic numerals. As you know, back then, banks were collecting money, merchants were trading, employees needed to be paid, ships were sailing, and many other systems that need a robust number system. And that's how Europe shifted from the Roman numerals to the Hindu-Arabic numerals. And with that, I stop here. I will definitely make a second part to this video. Until then, subscribe!